Merci beaucoup. Hi, everybody. I'm Denny, and
Hi, everyone. I'm TD.
so today's session, even though it says on the outside Delta Lake overview, no, we're actually going to talk about Delta Lake 2.0. You have questions. We are here to answer them. Hopefully, most of them are correct. So we'll go from here. So even though it seems like a marketing slide, because every single Databricks session will always have this particular slide that talks about the lakehouse, it's actually important to talk about lakehouse within the context of Delta Lake. And the reason it's important is because it's not just about, just like when Ali did his keynote this morning, it's not just about how, like for example, all these different companies are actually talking about lakehouses. Underneath the covers, when you actually want a lakehouse of any type, you actually need solid, reliable storage underneath all of that. And so Delta Lake is actually our foray into that, and of course with the community. And so that's why it's so important that no matter what you decide to do in terms of building your own lakehouse, why Delta Lake is so important is because it brings that reliability, that transactional protection to your data. And so, and basically I just summed it up like that, okay? So there we go. So the abridged version of this morning's keynote by Michael was basically, back in 2017, we realized that there are a lot of Spark jobs that were running that were actually failing due to many concurrent reads and writes going on to the same system at the exact same time. So we had to work around that problem, and then Michael Armbrust and the rest of his team, which includes TD here, okay, went ahead and recognized the fact that we had to build Delta Lake, a transactional storage. And so in 2018, during Spark and AI Summit, that's what we called it then, that's exactly what we did. We went ahead and introduced Delta Lake to the world. At the time, it was a Databricks-specific project, but nevertheless, we wanted to make it available for the world. 2019, the second phase of Delta Lake, is that we recognized that plenty of customers, whether they were Databricks customers or not, plenty of enterprises, small, medium businesses, they actually needed transactional protection with their data. So what did we do? We recognized that this was useful to everybody. We have friends from Ahana, friends from Trino that are all here, friends from Flink, they're all here. Why? They all have the same problem. They actually need transactional protection on their data. So we made Delta Lake open source and gave it to the world. But there was a little bit of confusion. Databricks kept on going ahead and creating awesome but performance features, but they were on the Databricks platform, not in the open source world. So that's what today's announcement was about. It was to say that, okay, let's remove all the confusion. Anything that says Delta Lake is open sourced, period. Now, we're not done yet. We're still in the process of open sourcing it, but the reality is all major features of Delta Lake have now been open sourced, or in fact, the Delta 2.0 release candidate that just came out this morning, thanks to the team, that actually has all those major features, okay? So that's the abridged version. You have any questions, you're more than welcome to ping into it, but now we're gonna talk about the Delta 2.0 preview right now. Those are the details that we'll wanna dive into. Okay, so I'm going to switch to TD, who's going to now talk about what is in Delta 2.0, and I'll add some color commentary.
All right. So a lot of new features has gotten into Delta 2.0. Some of it actually went ahead earlier in Delta 1.2. Over the last 1 year, we have been really focused on taking these features that were inside Databricks in DBR proprietary, where started open sourcing stuff. So I'm going to focus on few such features and do a deep dive in them in this talk. In the interest of time, you can always go through the release notes and the docs. And in fact, if you're more interested, you can always go through the design docs in the GitHub repository to learn more about the features, how it works inside. So let's start with one of the features called data skipping via column stats. So column stats is basically this additional indexes or indices that we keep related to every file and every column to track that for each column, what is the minimum and the maximum value present in each file. And using that, what we can do is that at the time of reading, doing a read query, let's say there's a read query which wants rows that have year particular value and a UID particular value, we first look at these column stats, the min-max values, and see, can this file even have this filtered values or not? If it cannot, then we don't need to read this file. So that's how we do data skipping, like entire file skipping based on the filters in the read query. And now these column stats are automatically generated. Starting 1.2, column stats are automatically generated when you're writing out those files into Delta table, and the read queries will automatically use those to do file skipping as needed. Now, for those who are familiar with like Parquet row group skipping and stuff like that, this is much better than that, because with Parquet row group skipping, you have to still read the Parquet footer for the row group information and stuff. You need to do the S3 call, cloud object storage call to do that. But here, you don't even need to do that. All that information is stored in the Delta log, along with the list of files. For each file, here is additional metadata information of column min maxes, et cetera. So even without touching the cloud blob store or HDFS and stuff, you can eliminate reading that file. So it's much better than that. But now, this works very well only if the range of values for each column in each file is small. If every file contains all values from 0 to infinity, you can't skip any file. So to make this skipping very efficient, you need to make sure that each file contains only a small range of values for each column. And that's where you need to do clustering, data clustering, or data sorting. Now, sorting has been there for a long time, traditional sorting, but while it's easy to sort, but it's not very effective whenever you have to scale to cluster beyond multiple columns. Here's an example on the screen where if you just do linear sorting, you do sort it in a certain way, but it's not very effective, because if you have to filter by that column that you're sorting by, great. But if you have to filter by multiple columns, not the best. Let me show you in the next page. So if you look at on the left-hand side, if you have a query which says select where X column equal to 2 or Y column equal to 3, then you want to read a certain set of files. Now, if you use just simply sorting by X, then you'll be reading a lot more files compared to this other way of sorting, which is called Z-order. Basically, there's a class of these ordering algorithms called spatial curves, and Z-ordering is one such spatial curve. But what it does is that it's basically a fancier form of sorting using multiple columns, such that the range of data for all of those columns in each file is small. So that means that no matter whether you query a filter by one column or another column or both, your list of files you have to read is much smaller compared to just single sorting. Now, the cool part is that now we have open source this command called OPTIMIZE ZORDER, where you can take a table and run that command, and it will rearrange the data in the table or within a partition based on the columns you specified. Let's say if you say ZORDER by X and Y, it will reorder it by X and Y. And so based on your reading query patterns, you can specify which column to Z-order by. And the other additional cool thing is that you can evolve this. If your query pattern changes, for example, your old queries used to be by column X and Y, new queries are now on column Y and Z, then you can rearrange the data once again in order to take advantage of that. So you can, this data layout evolution is much better than the old school partitioning and stuff, but provides the similar performance benefits as partition pruning and stuff using Z-order. The results speak for themselves. So along with Z-order in 1.2, we also released optimized compaction, where you have a single command that can compact multiple files into multiple small files into larger files. So here's a simple benchmark. I took the 3 terabyte TPCDS data set. One of the largest tables in that is a 0.5 terabyte table. To simulate how such tables form by repeated ingestion, I broke down the table into 40,000 files, 13 MB each. Having small files like that affects read query performance, because the overhead of reopening and closing small files adds up. So if you do compaction and it compacts them into 1 GB files, the read query definitely improves. But if you Z-order them further based on this query that I have, which looks for one column value, it becomes way, way better. So, and this extends to multiple columns as well. Moving on. the other cool feature that we just released, in the process of releasing in 2.0, is change data feed. And let me first talk about what is the motivation, why this feature is important. So it's a very common pattern called change data capture, where you have changes coming in from, let's say, some OLTP, transactional database, MySQL, Redis, whatever. And you want to apply those changes into a more OLAP-style database, like based on files and stuff, so that you can do analytical queries on that. And so to enable that, we initially added this merge operation in Delta Lake, a very efficient merge operation, where you can take those changes, row-level changes like update, insert, deleted, and apply them into a Delta Lake table. And in order to make that very flexible, we really push the boundaries on what are the syntax we support in merge. In fact, we were the first system that proposed additional syntax beyond the SQL standard in order to make common workloads much more flexible to add and stuff. We added that to Spark. We worked with the community to make all of that happen. We also have SQL API, Python API for doing merge. So that's well and good, but I digress. The focus is not on merge. But merge solves only half of the problem of the end-to-end goal of building end-to-end incremental pipelines, where you want to merge changes into a Delta table, and then you want to propagate those row-level changes to further tables. Like one common architecture is where you have layers of bronze, silver, gold, medallion architecture. There are different names to it, but it's common to have this sort of multi-stage pipeline. You want to make end-to-end incremental pipelines to propagate those row-level changes. So having efficient merge solves only half of that, because since merge right now, using copy on write, rewrites entire files, even if to change one row, reading only those changed rows is inefficient. And it's actually hard. Like, for example, if some row is deleted by the merge or some delete query, so that row doesn't exist anymore in the final table, how do you identify what are the rows changed? So you could join between two different versions of the table to identify what has changed and stuff, but that is also not efficient and still really puts the burden on the end user to find those differences and stuff. And that's why we built change data feed. And the idea is that while you are merging and rewriting the files for the actual final data, you're also saving the changed rows that were updated, inserted, or deleted in a separate set of files simultaneously. And this is fully transactional, same ACID guarantees as Delta and stuff. So we maintain this additional set of change files to keep track of the row-level changes, so that you can, if you choose to, you can just read them. So, and this is efficient in terms of reads, because when you don't care about the change files, you want to read the actual data, those files are exactly as it would be without change files. No need to filter out data. But if you want to read only the changes, you can read the different set of change files efficiently without need for additional filtering. So this solution you can use, you can optionally enable this on a table to make sure that all merge, update, delete, all these queries additionally produce these change files. And then you can run both batch and streaming queries on top of them. Basically, for building incremental pipelines in an end-to-end streaming fashion, we have added streaming support. It's very simple. When you're starting a streaming query, when you're reading from a Delta table, you just add an option saying read change feed to true, and it will read only the row-level changes and not all the files that have been modified. And then if you want to query, give me all the rows changed between two versions of a table, either version by timestamp or version number, then you can just do a data frame query. As of now, you can do a data frame query. Eventually, we will have SQL support as well. That's coming in future release.
All right, so we've already just flooded you with the optimize zorder and change data feed stuff. We have a lot more too, so wanted to pause for a second. Does anybody have any questions just on those two concepts?
I see one hand there.
Yeah, so a quick one. When you do the update and you record it in transactional table, do you actually save the old value and the new value, or just the new value?
Both.
Both. Because
So-
I see just it's like one line here.
Good eye, good eye. So basically, because of I blame the lack of real estate on slides. But look at the docs and stuff. But yes, we store both the pre-image and the post-image. So when you query, you will actually see 2 rows for an update.
Any other questions?
Any more questions?
Okay.
Okay,
All right, let's do it.
moving on.
No, you
yes,
covered
we
that
have covered
one.
this.
Yeah, column mapping. Yeah.
Yes, the other big project that we did over the last year is this column mapping project, which solves a different problem. Now it's a metadata schema management problem. So earlier, in Delta 1.1 and below, we basically, for any column, say A, the way we stored that data for column A was that we had a Parquet file, which also had column A, which basically means that we were, there was no separation between the logical name A and what is the physical name that is stored in the Parquet file, which basically means that we were limited in 2 ways. One, Parquet file format has limitations on what is the set of characters that are supported in the column name. It doesn't allow commas and stuff, for example. And then the second limitation was that how do you reason about removing a column? Like if you want to rename a column, drop column, you cannot rename a column without rewriting the entire set of files. So to solve those 2 problems, in 1.2 and above, we introduced this logical to physical column name mapping as a simple indirection, where even if you say, I want to create a table with column A, internally, if column mapping is enabled, you will, the files will have store the values of column A as a UID. So that is the physical name of the column, which means that because of the indirection, it's very easy to rename the column A to column B because we just change the mapping. So instead of A, just B points to column UID1 in the actual physical files. And that also means that we no longer have the limitation that we support commas and semicolons and all the things that Parquet column name doesn't support. So with this 1.2, we introduced rename support and having arbitrary column names. With 2.0, we are releasing dropping column support as well. Any questions? Cool. Moving on. Now moving from APIs to infrastructure. One of the biggest advantage of Delta Lake is that to get our transactional guarantees, we do not depend on any distributed locks or distributed leases or depending on some self-managed infrastructure like Hive Metastore, et cetera. We rely on the transactional guarantees given by the file system itself. So things like HDFS, Azure Blob Store, GCS, they provide APIs with which you can say that when there are 2 concurrent writers trying to write to the same log file, in this case, let's say there is log files 010, which is like 2 commits made to a Delta table. If both concurrent writers are trying to write version 2 by creating 002.json, only one of them will succeed. And the other writer will have to retry and commit its changes by writing 003. Now, what this ensures is like a full serializable log of changes. And so this is what gives us the full ACID guarantees all the way to the at the SQL command level. So now this basically relies on the extremely scalable cloud blob store infrastructure as well. So no additional infrastructural requirements, no leases, no distributed logs, which are notoriously hard to get right and not have deadlock issues or not have timestamp skew issues and stuff. Now, the sad thing was that S3 of being one of, even though it is one of the oldest blob stores out there, did not support any API by which you can create this file atomically only if it is absent. So as a result, what would happen is that if there are 2 concurrent writers trying to write to the same file, both will succeed and they will overwrite each other's changes, therefore losing serializability, asset guarantees, and stuff. So before Delta 1. With Delta 1.1 and below, we supported concurrent writes only from one single cluster on S3. With 1.2, we added a new solution using DynamoDB in the picture, where instead of trying to transactionally write to S3, we first transactionally write to DynamoDB. So now, just to be clear, this is not, we're not holding a lock, we're not holding a lease. We're doing basically a transactional put a key in DynamoDB only if it is absent, the key being the version. So we're using DynamoDB as the serializer. And so only one of the writer wins when trying to create version 2 in DynamoDB. But after we have committed 2 to DynamoDB, the writer, in this case an entire Spark cluster, once it will sync those changes all the way to S3 as well, so that any other reader reading the Delta log in the file system directly has the consistent view of the entire table. So this solves this multi-cluster write problem on S3 without using any distributed logs, distributed leases, or without requiring any additional self-managed infrastructure. You're using an extremely scalable managed service, DynamoDB, and everything just works. All you need to do is basically write a few Spark configurations to specify the log store type. I won't go into the details of what is a log store, but you specify basically use DynamoDB, and here is the DynamoDB table details, and you're good. That's all you need to know. All you need to configure. Well, you have to make sure that all writers to the same Delta table are configured to use the same DynamoDB table. But this solves the multi-cluster write problem on S3. So as I said, there are a lot of features that I will not have the time here to go through. Please look at our release notes. Rather, I would focus a little bit of time into how we are expanding this Delta ecosystem beyond Spark into other engines. This is a lot of effort that has gone into over the last 1 year since the last summit. We have added support in Flink, specifically Flink. We've added Delta Sync in Flink, so you can use Flink to write into Delta tables using on ADLS, GCS, S3 single cluster right now, but multi-cluster. The same solution I talked about coming in the next release. And it's scalable, same with Spark. Like it's at the same level of support as Spark right now already. With Flink, Delta source is being built right now. We expect it to be released in the next couple of weeks. But it's cool that it is, for both of these, we support both batch and streaming in sync and batch and streaming in source. We support doing time travel queries. So you can, in batch, you can query older versions of the table by version number or timestamp. For streaming, you can choose to either read the entire table and changes, or just changes from a particular version, or just new changes. You have the entire flexibility, same as our Spark in Spark streaming support. So we have brought it up to the same level of support, both in Flink and Spark. What is missing and it's in progress is basically Flink SQL and table API support, catalog support, but that will come in the next 3-4 months. Further on, Trino, Presto, we added support for Delta reads in both Presto and Trino at a particular version number. Trino, in addition, supports data skipping with column stats. That's the stuff I talked about. It supports writes with transactional guarantees, and also supports optimized compaction stuff that I briefly talked about. So, and we are not done. We are obviously expanding the support. Flink, Trino, Presto has been our focus right now, but we are going forward. We're going to work with the Pulsar folks. They are interested. We're going to work with Google BigQuery, and we're going to work with so many, all the other people who want to read-write Delta tables. And the common underpinning of how they are reading the Delta log is this project called Delta Standalone. So basically, Delta, all the features, when we say Delta, we're tied to Spark. So there is a Delta Spark implementation, which implements the Delta on disk protocol. And then this is an independent implementation unrelated to Spark, no Spark dependency, pure Java that can read the Delta log files and expose it programmatically. And all these projects like Hive support, Presto, Flink, all of these are essentially using the Delta standalone, it's Java, to read and write the Delta log from these connectors. So this is the underpinning of all these connectors, and we hope that this, as we improve Delta standalone to be at the same level of support as Delta Spark, Delta standalone is much newer than the Delta Spark thing, we will grow the ecosystem. So you let us know as a community what we need to add in Delta standalone. It will help us prioritize the work. And speaking about community, back to you, Denny.
All right, thank you very much. Now, one thing I do want to stress, when you look at, before I go to my own slides, when you look at this particular slide, we talked about S3, we talked about Presto, we talked about Trino, we talked about Flink. This wasn't just done by like the Databricks Delta Lake engineering team, okay? I don't want to diminish any of the work they did by any stretch of imagination, but the thing that I want to overemphasize is this is help from the community. So we have some of the Trino folks here, we have some of the Ahana folks here, Flink folks from Vivarica, the S3 folks, Samba TV. So we had community help on everything, okay? So we are better not because of just us as in TD and me standing up here, right? We're better because the community works together to make these projects significantly better together. This is how cool the numbers are. You might have been able to see it properly during Michael's keynote, but here's the call out, okay? We went from 650,000 downloads in May of 2021 to 7 million monthly downloads in May of 2022, okay? So that's a 10, 11x improvement in downloads in less than a year.
Denny, by the way, these numbers are already stale. We made this slide 2 weeks ago, and the number is already more than 8.5 million.
Yes, fair enough.
In the last 2 weeks, we have our PyPy numbers went up by more than 1.5 million.
So, but the important call out is you notice that it looks like it's a crowd, but actually it's purposely done this way, okay? The reason why is because look at all the releases we have. We have a bunch of ones for Delta sharing, or for Kafka Delta ingest, for Delta Rust. The Python bindings for Delta Rust actually come out literally every 6 weeks. The Presto implementations, the Trino implementations, the Flink implementations. So there's a lot of activities from the community itself, all right? Yes, we get to be lucky enough to go ahead and help guide it, but it is a full-blown community effort, and that's why the numbers are so big. It's not just about individuals, too. We have developers from all of these different organizations that have contributed to Delta. Okay? There are more than 70 developers from more than 70 different organizations that have actually contributed to Delta. So, in fact, we were surprised. We didn't know that, actually, when we actually originally were looking at the numbers. And so we want your involvement not just to go ahead and say use it. Don't get me wrong. Absolutely love the fact that you're using Delta Lake, okay? But we want you to contribute to Delta Lake. Tell us, it could be as simple as documentation or telling us what the problems are, because I'm sure we're not all infallible. But we'd love you to also go ahead and give us PRs. Make suggestions on what we should go improve and work on. There's a lot of people working on all these 6 different repos right now, okay? Delta's not one repo, it's 6 right now, and we're probably gonna need to add more. Now, for some people, they're saying, oh, that could be so much simpler if you just one repo so you can count the number of organizations or the number of people. We're not interested in doing that count just for the sake of doing the count. We're interested because each one of these projects runs actually at a different pace and are being guided by different people. The Delta Rust project is being run by the folks over at Script and Backmarket, for example. All right? The Delta Connectors is being run by God knows how many different people at this point, okay? So each one of these projects are running at a different pace, and that's on purpose because we are going, the pace of innovation for Delta Lake is that fast, and we want to keep up with whatever the community wants us to do. So if there are more projects that people are interested in, okay, for example, like TD had mentioned, there's the Golang one. Oh, sorry, the Google BigQuery, excuse me. Golang actually is one that's actually people are starting to work on. So we might actually have to create yet another repo just because there's actually active work on Golang itself as well. All right? So let us know. And then that leads me to this slide. Very simple, okay? How do you want to contribute, okay? We have lots of good first issues. You literally go to our GitHub. Each one of them, we tag good first issues. Go ahead and look at them, all right? Go ahead and join us in the Delta user Slack. I've got another screen that actually shows that. It's basically go.delta.io/Slack, but I've got another screen for that. But we actually have a contributors channel. So if you got questions, just ping us there directly. Now, we're pretty active on GitHub issues, GitHub PRs, Stack Overflow, Google Groups, and all these other places. But the point is that if you want specifically on contribution, talk to us there. We're pretty active, okay? And of course, check out Delta.io. We constantly update that with information. Here's another really cool contribution. We just tossed this slide in literally today, okay? The reason is because the folks at DataBeans, okay, independently, we did not help them with this, okay? They independently ran their own benchmark, comparing Iceberg, Hudi, and Delta Lake. We did not ask them to do it, okay? This is not something we told them to do, okay? They were just simply interested because they had their own customers go do this. And so the link, by the way, the slides are available, so you go ahead and take pictures, but you can download the slides, okay? We have the link to their blog right there, but it just showcases how much faster Delta Lake is. It's 1.7, from their tests, 1.7x faster than Iceberg, 4.3x faster than Hudi, okay? And so this is an example of their contribution, because they're actually going to be creating a couple PRs specifically to merge back to Delta Lake. We actually had a benchmark set of code there that was actually just comparing Parquet and Delta Lake. Well, they're putting in the Iceberg and they're putting in the Hudi code base as well. All right? So I do want to leave with this basically here, right? Lots of ways to work with us, okay? In GitHub, Slack, Twitter, we also have LinkedIn, but just go to delta.io. The number one place outside of the website itself easily is Slack, which is go.delta.io/Slack. Just join there. We're all of us are here. The Delta ecosystem team that sits back there, they're also on there as well. So we are there to answer your questions. If you've got some really good ideas, we'd love to listen to them. You've got some PRs you want to do, we absolutely would love you to go do that, okay? So we've got 3 minutes left, okay? So I think if you have any questions, we can be up for 3 minutes before they kick us out. Any questions?
Wow, our talk was so
apparently,
clear.
I guess so, yeah. All right, go for it.
I see two hands over there. Okay.
So you were showing how you could optimize that query, the z-order, with the z-order filtering using the x equals 2, y equals 3. And I was kind of wondering, I think that could also be optimized with like directory partitions. So like when do you lean towards directory partitions versus z-order indexes?
Very good question. Shall I take that?
Yeah, go for it.
Okay, cool.
Yeah.
So partitioning is great in terms of filtering, but the downside of partitioning is that once you have partitioned the table, you really can't change that without rewriting the entire table. Whereas with z-order, since it's not partitioning, it will give a pretty good filtering, just like partitioning, because if files have small boundaries and stuff, but it does not limit you from having to rewrite the entire table based on if your query patterns change and you wanted to rearrange the data by a different set of columns. So that it gives you that long-term flexibility. In practice, you can actually use them together. A very common pattern, for example, is that you have data coming in across multiple dates, like daily logs coming in, and so you partition by date, but then you may have different query patterns for older dates than newer dates. So you could rearrange the partitions of the older dates in a different way than the newer dates using z-order. And as new dates become older dates, repartition again and move on. So there is scope for evolving the data layout with time, which you do not get with partitioning.
Cool, I think there's one question here, but as he came up for the question, I did want to remind, we actually have 3 events tomorrow that you guys probably will be interested in. One is that we have the Delta Committers AMA at 11:40 in the Expo Theater. The second one is a 4 p.m. Delta Lake Open Source Contributor Happy Hour. Yes, there are drinks. So please come to us. We're at the Intercontinental. By the way, Dom from Apple and Michael Armburst are going to be there to also do a quick AMA there. And then at 6 o'clock, sorry, 6:30. I wrote down 6 o'clock, but it's actually at 6:30. We actually have a meetup here in Moscone, okay? Room 153, if I recall correctly. It's the Delta Lake committers meet and greet. So a lot of the committers, you're going to meet them all here. And birthday party. So yes, we have got cake. So, all right? So just quick call out. Sorry. Yes.
All right. So with the change data feed, so if we use streaming or if we use Delta Live tables, we'll be able to incrementally push data across layers, bronze, silver, gold, right? But if we use the batch way, we have to maintain control tables, and we have to maintain timestamp for the last load, and then look it up, and then say, OK, give me data after that timestamp for this particular table. So I have to technically maintain a control table for all tables that are in the pipeline, right? Are there any plans to build a feature that does this mapping if we enable change data feed so we don't have to maintain control tables?
OK. Let me try to understand what you're trying to do. So you're saying that you want to, instead of using structured streaming to read change data continuously, you want to have your own process that uses batch APIs to read a range of change data. And you want to have additional table to track which which timestamp maps to what?
Yeah. So let's say we're doing this load every 10 hours or whatever, right? I have to say in a control table, OK, I have read from this table, the last read was as of this timestamp. So if there are 10 tables in the entire pipeline, I have to say the last read timestamp and maintain in the control table. So the next time I run it, it will look up the last read timestamp and take the changes after that, right?
Yeah. I mean, you could do that. I'm just trying to understand why would you do that if structured streaming exposes that, does that tracking of what has been read for you?
Yeah, that's what. So if I use structured streaming, I'll have to change the code a bit and then follow the structured streaming syntax and all that. But I'm just trying to see if there's anything in the roadmap with change data feed that's going to do this. Delta Live tables makes it easy with the incremental syntax.
Sure. See, the thing is, so let me understand this. So you want to maintain your per app metadata of how much has been read. That is so application specific that it's hard to put that information in a common Delta table. So we could add more features. Maybe we can brainstorm this offline on what exact feature that could be added in the Delta Lake table that could make this easier for management. And if there is something, definitely, we are totally open of doing that so that structured streaming need not be the only way of doing this. Absolutely not. That's why we're working on Flink and all that stuff. So anything that will help any processes to read change data feed more efficiently and that helps your application, well and great. So let's chat offline about this.
Awesome. Cool. No worries. Thanks.
All right, so we actually do have to shut down. So thank you very much, everybody, for attending the session. Hope to see you at the party tomorrow. You and I actually need to run.